Rightio, g'day students, welcome to our 6th lesson in organic chemistry. Today we're looking at boiling point change, melting point change and the volatility of various organic compounds. So the point of today's lesson is that you should be able to recognise that organic compounds display characteristic physical properties, including melting point, boiling point and solubility in water and organic solvents. We'll look at tomorrow those. That can be explained by the intermolecular forces, which are dispersion forces, dipole-dipole interactions and hydrogen bonds. And they are influenced by the nature of the functional groups as well. We should be able to predict and explain the trends in melting and boiling point for members of a homologous series and discuss the volatility particular of alcohols, aldehydes, ketones, carboxylic acids and halides. Just to take you back to Unit 2 when we're looking at intermolecular forces, remember we were looking at forces between molecules and we classified 3 of them. We said, well, there were dispersion forces, dipole-dipole and hydrogen bonding. And we noted that hydrogen bonding was the strongest type of intermolecular force. If we were to just revise that again, just remember that a dispersion force occurs between all molecules, no matter whether they're polar or non-polar. Now, they're caused by temporary dipoles, which are in the molecules as a result of random movement of the electrons surrounding molecules. Now, when comparing molecules of the same molecular mass, the dispersion forces are generally weaker than dipole-dipole forces and hydrogen bonding, and they are the weakest of the intermolecular forces. Now, dipole-dipole forces occur between polar molecules and they result from the attraction between the positive and negative ends of polar molecules. Now, they're stronger than dispersion forces, but they're much weaker than hydrogen bonds. So finally, if we think about hydrogen bonding, this is a particularly strong form of dipole-dipole force. Hydrogen bonding occurs between highly polar molecules in which a hydrogen atom is covalently bonded to, so we've got a hydrogen, to oxygen, nitrogen or fluorine. So there's a big difference in electronegativity there. So hydrogen bonding is the strongest type of intermolecular force, and you'll recall that hydrogen bonding occurs in water, and that's what makes water have such a high melting and boiling point for its molecular mass. And hydrogen bonding is what the strongest intermolecular force. So remember, it's occurring between these unbonded electrons, which is the negative. So we've got a partial negative, that's that capital sigma, and the partial positive of the water molecule. So that's that one there. If we have a look at a homologous series, we know that organic compounds with stronger intermolecular forces require more energy and therefore will have higher boiling points than organic compounds with weaker intermolecular forces. So if we have a look here at the alkanes, what we've got, methane, it boils at negative 162 degrees Celsius. So that's explained by just the dispersion forces holding it together. As you increase what's happening to the boiling point, if you increase the carbons, we're going from 1 to 2 to 3 to 4 down to 10, there is an increase in boiling point. Now, this is explained by the dispersion forces being the only molecular forces in alkane molecules. As the molecules become longer, their contact surface area increases, increasing the dispersion forces. So boiling point increases as the length of the carbon chain increases because the dispersion forces acting on the molecules get stronger. Now, I should also note that branching decreases the amount of contact between the two molecules, and therefore if there's increased branching, there's decrease in boiling point, and this is what we're seeing here. You can see that we've got butane and methylpropane, and they're both C4 molecules, H10, and because we have this branching, we have a decrease in the boiling point. If we have a look at aldehydes, ketones and esters, Can I turn that camera off? No, I'll just put it to the back. The presence of the carbonyl group. So remember, carbonyl is carbon double bonded to the oxygen. You're going to get this partial negative on the carbonyl. And what that means is it can bond to the partial positive, for example, on a carbon. So the presence of this carbonyl group enables the formation now of dipole-dipole intermolecular forces in the liquid state. So if we have a look now at each of these homologous series, which ones of these have the carbonyl groups? The aldehydes, ketones and esters. Remember, the alcohols have the hydroxyl group and they're going to form hydrogen bonds. We'll look at that later. But you can see that these three with carbonyl groups are intermediate in their boiling points, certainly stronger than the alkanes, which only have dispersion forces. But if I look at the alcohol, that has hydrogen bonding. We'll look at that later. Okay, so aldehydes, ketones and esters have higher boiling points than hydrocarbons of similar molecular mass, but lower boiling points than alcohols. So if I have a look at the als, so they're aldehydes, that's aldehyde, meth, eth, prop, bute, pent, so the 1, 2, 3, 4, 5. What's happening to the boiling point? As the carbon chain increases, so does the boiling point. And you can see that at room temperature, there should be room temperature, that should be liquid, and that will be gas. Okay, now if I have a look at alcohols, carboxylic acids, amines and amides, we're going to first of all note that each of these four have hydrogen bonds. So alcohols, carboxylic acids, amines and amides have high boiling points because their molecules can form hydrogen bonds with the neighbouring molecules. Now hydrogen bonds, remember, are the strongest of the intermolecular forces. So if I have a look first of all at alcohols for this slide, you can see that we've got an OH group here and OH group here. And what's happening, you can see this hydrogen bond along here that is connecting to the partial positive and the partial negative. Now, we should also note the effect of branching. So increased branching in alcohols results in decreased boiling points. And that's because that hydroxyl group is becoming increasingly crowded by the alkyl groups, which are these ones over here. So it's hard for them to actually form those hydrogen bonds because they're getting crowded out. So as the branching increases, the boiling point decreases. Now, let's have a look at amines and amides. So in amines, the hydrogen bonds form between the non-bonding pair of electrons of the where they're on the electronegative nitrogen atom and the partially positive hydrogen atom. So there's our partial positive here, that's the sigma plus on the hydrogen atom attached to the nitrogen of the other amine molecule. Now in amides, what's happening? So the hydrogen bonds form between the non-bonding electron pairs and the oxygen atom and the partial positive of the hydrogen atom attached to the nitrogen of the another amide molecule. So here we go, and there's our bond. Now the strength of the hydrogen bonding between the molecule explains the relatively high boiling points of amines and amides when compared to hydrocarbons of a similar molecular mass. So what do we got here? Amine, amide, and we've got the molecular mass around 60 for each of these, and you can see that amine, boiling point, amide. So they have, certainly compared to alkanes, a much higher boiling point. Yeah, and we'll leave that there for a moment. Let's talk about now carboxylic acids. These guys are interesting. They form dimers. And essentially that's where two molecules present as one molecule due to a strong intermolecular force, and that strong intermolecular force is, of course, the hydrogen bonding here. So if we've got two ethanoic acid molecules, instead of presenting as one ethanoic acid molecule, it's going to present as a double. So it's a dimer, and that's due to that hydrogen bonding there. Now that's going to double the molecular mass to a single unit, and also going to enable the formation of stronger dispersion forces, as each dimer has a larger surface area. So this presence of the hydrogen bonds and the dispersion forces explains the higher boiling point. And you can see that in comparison with alcohols, for example. So carboxylic acids have the highest boiling point of each of them. So here's our ethanoic acid for a mass of 60, compared that to propanol, and you can see that a similar mass, we've certainly got a higher boiling point compared to all that. And now let's have a look at propanoic acid, which is our 3 carbons, so 3 carbons there. You can see that the carboxylic acids are higher. Let's have a look at this one for butanoic acid, and again it's higher than the others. So that presence of the dimer, which is what, due to the hydrogen bonds, means that it's essentially got the highest boiling point of any of the families we've been discussing. Now if we look at trends and melting points, it's quite similar. The general trend for a homologous series is that as a carbon chain increases, the dispersion forces acting on each molecule get stronger, resulting in an increased melting point. And you can see that, but there's some unusual exceptions. So let's look at propane. So this trend is not as regular as in boiling points due to the packing or the way that the molecules are arranged. And you can also see a big gap between the odd and even molecules when they are here. So you can see there's a big jump from C7 to C6, and from C5 to C6. You can see that there's a bit of a jump in comparison to the others, and that's suggested to do to the packing. Now, if we have a look at volatility, if I smell a fruit, it's got some volatile oils in it, and that's what gives off fruit its characteristic smell. Also, petrol. So petrol is generally octane, isn't it? And it's quite a volatile liquid, so it forms a vapor easily, which means you just smell it. Okay, so volatile substances contain weak intermolecular forces. So we're expecting small non-polar hydrocarbons, i.e. things like methane, so alkanes and the meth groups, so meth, etc., the smaller ones, are going to be able to evaporate more easily. And that's, as we noted, due to the intermolecular forces. So the alkanes have what? Only dispersion forces acting on them. Now, if a haloalkane, you're going to form a polar molecule, aren't you? So if you put a halogen in there, or a chloro or a fluoro, etc., you're going to be able to make that a dipole-dipole bond, and that came out really weirdly. And so that's going to increase the volatility. Decrease the volatility. It's going to make it less likely to evaporate, and that's due to those dipole bonds. Now, alcohols, remember, have hydrogen bonds. So do carboxylic acids, but let's go a different color. So both alcohols and carboxylic acids form hydrogen bonds, but recall that carboxylic acids also present as dimers. So they are presenting as two molecules in one, and there's going to be an increase in those dispersion forces and hydrogen. So that's going to reduce their volatility as well. We've done a little bit today. Are you able to recognize that these organic compounds display characteristic physical properties, particularly looking at melting point, boiling point today, and volatility, and that can be explained in terms of those three intermolecular forces we've talked about: dispersion forces, dipole interactions, and hydrogen bonds. And that's influenced by the nature of those functional groups on them. Now, can you look at a homologous series and predict and explain the trend in the melting and boiling point and discuss the volatility of those as well? When you're done now, I'd like you to work on the mastery questions, please, students.